All right, great. Thank you, Julia. I'm Allison Melton. I'm the Education Outreach Specialist at ORNL in Oak Ridge, Tennessee. We're excited to start our own SAGE camp this summer for kids and for girls in Tennessee. So we're able to expand SAGE across the country. We're excited about that. I'm going to introduce our speaker today. Our speaker today is Katie Schuman, a former research scientist at ORNL and a current assistant professor in the Department of Electrical Engineering and Computer Science at the University of Tennessee in Knoxville, Tennessee. She grew up in Harriman, Tennessee, before earning her bachelor's in computer science and mathematics and a doctorate in computer science at the University of Tennessee. Her research interests are neuromorphic computing, deep machine learning, and data mining. In her free time, Katie enjoys reading, playing board games, and traveling when traveling is an option. And I'm excited to see what she has to say. So please help me welcome our speaker, Katie Schuman.
Thank you, Allison, and thank you for the invitation to talk to y'all today. So I am going to have some slides, but at some point we're also going to be playing a little bit with AI and machine learning today. So I hope you all will join in with that. So I wanted to tell you just a little bit more about myself, and I will caveat this by saying I am currently in Harriman, Tennessee, where I grew up visiting my parents. And so I apologize if there's chaos around me at any point. You may hear a wide variety of different sounds. So I spent 6 years at Oak Ridge National Lab as a researcher working in AI and machine learning. In particular, I was part of the nature-inspired machine learning team, and I got to do a whole lot of cool things with different scientists around the world, including at other national labs like SLAC and Fermilab. In fact, I just mentioned to Jen that I was working with researchers at Fermilab on some of the scientific data that they were generating. One of the cool things about being in a national lab and working with AI and machine learning is that we had really big computers that we can do AI and machine learning on, like the Summit supercomputer that you can see me standing next to. There, you can only see a very small portion of the computer. There's a lot more of the computer in a much larger room in that space. So I really love doing things like this and talking to students like you, which is why I've now gone back to be a professor at the University of Tennessee. And I co-founded the Neuromorphic Computing Research Group there, and you can see some of the students and faculty who are part of our research group. If you are interested in learning more about my research and what we do in this in-lab group at the University of Tennessee, please reach out to me. I'll have my contact information at the end. So I actually studied computer science and math as an undergraduate at the University of Tennessee. I didn't actually start playing with AI and machine learning until I was a senior, and it was sort of before AI and machine learning became really, really popular as a field. It was before it really blew up in success. But then I did my PhD in computer science focused on machine learning, and in particular a type of machine learning that I'll talk about later. And so I've been studying this for over a decade now and doing research in developing new ways to do AI and machine learning. So in my free time, I do like to travel, and I'm a giant geek. So I'm a big fan of Star Wars and Harry Potter, and I really like going to Disney World and various other locations. And that's my dog down here, the German Shepherd there. She's in this house right now, so if you hear a dog barking, that's her. You can see she might actually jump in my lap at some point. So actually, my love of Star Wars is very much related to my passion of AI and machine learning, because I also love robotics. And so the idea of having a droid like R2-D2 being an intelligent companion is something that is really fascinating to me. And you'll see that some of my work plays a little bit with robotics later on in the presentation. So what does my job as a computer scientist and a professor look like? What does it look like to do machine learning research? Well, most of my job is actually writing code to do machine learning. So I can do my job from just about anywhere. As long as I have my laptop, I can do my research. I actually spend a lot of time talking to different groups, now teaching as well, in talking about my research. And actually this semester, I'm teaching machine learning to students at the University of Tennessee. But I also get to collaborate with a lot of other researchers and scientists working across a wide variety of domains. So Jen, you might recognize this is me at Fermilab visiting the Minerva experiment. I worked with some of the researchers on the neutrino data that they had collected. And sometimes I get to go visit and learn about all of the different sciences and physics and chemistry and biology and material science and all sorts of wide domains of interest that are really cool to me to learn about. And I get to bring my science, machine learning, to help try to do something with those scientific data sets. So my job also takes me to a lot of fun places. It's really fun to be a researcher, and hopefully soon we'll be able to travel again. As Allison mentioned, I really love traveling. So I've gotten to go to places like I'm in Budapest, there in the bottom, Alaska. There's me with a bear in Alaska, Italy, Japan, and Amsterdam, and among other places. These are just some of the favorite locations I've been able to visit. And I really hope I'll be able to travel again and hopefully maybe even get to come out and see some of you all in California sometime soon. I miss traveling very much. So that's a little bit about me and my background and what my job sort of looks like. But what is machine learning? So as part of the Sage Camp, I'm assuming you've done a wide variety of different types of science and technology. And maybe you've done some coding before where you've written maybe a program or something like that to have a computer perform a particular task. Well, typically when you're writing computer software, you're telling the computer a list of instructions to follow to complete the task for you. So let's imagine, before we talk about machine learning, that you are going to write a program to have a computer look at a picture and tell you if that picture was of a pig or if it was not a pig. So first point of interaction, I will ask you to maybe put in the chat, what are some things that you might write in your instructions for the computer to look for if you were looking to teach it to recognize what a pig looked like? Are there any features of the pig you could tell it to look for if you were trying to teach it? Maybe you could put some answers in the chat. Let's see if I can pull it up. Tail, nose, ears, pink, looking for that snout, the hooves. Yeah, all of those things. You could sort of code that in to say, okay, I need you to look for these sorts of features. And if it has those features, then it might be a pig. Yeah, so absolutely, those are different features that you might be able to code in and say, okay, I'm going to look for that, and then I can have the computer figure out if it's a pig or not a pig. So traditional programming is about putting together maybe a list of rules and saying, okay, is it pink? Does it have a tail? Does it have pointed ears, 4 legs, hooves, and so on? And maybe you could turn that into code and have it check, okay, if it has these different features, you would say, yes, it's a pig. And if it doesn't have those features, then no, it's not a pig. Well, here's some situations that might fail that traditional coding. So these are pretty weird, I will give you that. Here is a car that has a snout and pointed ears, and it's pink, and it has something like 4 legs, although you can't see all of them. Actually, I suspect that this car would also have a tail if we could see the back of it, just by virtue of how detailed it is. And so maybe our computer program would fail on this and tell us that that is a pig, but we wouldn't want it to say it's a pig. It's certainly pig-like, but it's not exactly what we want to see. Here is another example of a pig acting very much not like a pig, but we would want the computer program to tell us that it is a pig. Here is a child that seems to really like pigs a whole lot, but again, we wouldn't want the computer program to tell us that it's a pig. And then here's a pig that sort of illustrates one feature of pigs, which is they aren't necessarily pink. The example that I showed you before was certainly a pink pig, but they can be brown, they can be black, they can have spots, they can have all sorts of different colors. And our computer program would almost certainly fail on this example of a pig as well, just because it's also, wearing glasses, which pigs don't normally do. So, okay, so now that we've seen these pictures, we could say, all right, okay, well, I could adjust my rules and sort of account for these weird scenarios to try to refine my computer program to make it so that it would better recognize pigs in the future. So how do you decide what the rules are actually going to be? Well, if you sat down and you started to think, okay, I'm going to try to come up with every possible condition so that if I showed the computer a picture of a pig, it would be able to get that correct. Well, anytime you would come across a new picture, maybe you're having to add new conditions, new rules, and that's a lot of work. And it's not going to be easy for you as a human to sit down and come up with what that should look like. So we're not going to do that. In fact, we are going to have the computer learn how to distinguish between various things, in this case, pigs and not pigs, with machine learning. So the idea behind machine learning is that instead of you sitting down and hand coding up all of the rules for what you want the computer to learn how to do, instead, we're going to give the computer examples of the data that we want it to learn about. So instead of maybe distinguishing between pigs and not pigs, maybe we want it to be able to look at pictures and be able to tell us it's one of these 10 different types of items: planes, automobiles, birds, cats, deer, dogs, and so on. So what we would do is we would give this data to a machine learning algorithm, and we'll talk later about what a machine learning algorithm looks like. But the goal is for us to be able to give this data to the machine learning algorithm, and the machine learning algorithm would produce a machine learning model. So you can think of the labeled data as like flashcards that we're giving to the computer. And we're saying, this is a plane, this is a car, this is a bird, this is a cat, and so on. So we're giving it the answer for our labeled data. And what we want the machine learning model to be able to do is to take a new picture that it hasn't seen before and be able to tell us what the correct label is for that picture. Now, why do we call it machine learning? Well, there's a big difference between learning something and memorizing something. So if you've memorized something, maybe you've memorized something like dates from history, or you've memorized your multiplication tables. If you've learned something, you have a deeper understanding of what's going on. So at some point in your life, you learned what a pig looked like. And even though you may have never seen that picture of the pig with the sunglasses on before, you could look at it and be like, yeah, that's a pig, because you learned intuitively what the features of pigs are so that you were able to recognize it. So with machine learning, we want the computers to learn from the data, to be able to extend to new situations that it's never seen before. So even though these pictures, these sort of silly pictures that I found of the dog and the cat and the bird and the horse and so on, were never seen by the computer before, we still want it to be able to give us pretty good answers. So you all have already done a fantastic job of identifying some of the places that machine learning is used in your talking about where you might encounter it every day. So one of those is in smart home assistants. I will not be saying any of their names so as to not wake them up in your houses or mine. But smart home assistants like the one that you see on the screen here, the one by Amazon, the one by a certain search engine, those use machine learning not only to take the sound waves that we're generating when we're talking to them and turning them into language that they can interpret, speech recognition, trying to interpret what we're saying. They also use machine learning to try to give you good responses back to maybe the questions that you're asking. Lots of different apps on your phone, including social networking sites, use machine learning. So a couple of my favorite examples: if you've used Snapchat before and you've ever used like a filter on Snapchat, maybe you've done something like put on cat ears or changed sort of your facial features a little bit, smooth them out in some way. Snapchat uses machine learning to identify where your face is to be able to correctly position whatever thing they're adding to your face or the filter that they're applying. Social media entities like TikTok, I actually think TikTok has the most sophisticated, at least from a naive user case, of machine learning approaches that they're using to tailor the feeds that you're receiving to you. It's learning about your preferences and adapting to be able to provide you videos or content that you would want to see in the future. Google and Amazon both use machine learning to be able to tailor search results to you. Amazon also uses it to be able to recommend future purchases. Somebody mentioned like Spotify, YouTube, Netflix, all of the sort of music and media sites use machine learning, again, to give you better recommendations about what you should watch or listen to next based on what you have previously listened to, but also based on what other people in the world are listening to, and they're learning from how other people make their choices to recommend new content to you. And then one of my favorite examples of use cases of machine learning is in autonomous vehicles. So machine learning is increasingly being used in commercial vehicles. A lot of cars that you would buy these days would have some sort of machine learning to help you drive, even if you're not driving completely autonomously yet. But autonomous vehicles of the future and the autonomous vehicles of today rely on machine learning to be able to perform well. And obviously, this is an ongoing area of research. They're not perfect yet. So we're still refining what the machine learning approaches should look like and how we should train them or teach them to be able to drive most effectively. So I mentioned that when I was an undergraduate student at the University of Tennessee, actually AI and machine learning still didn't work very well. The ideas behind how AI and machine learning work have been around for decades, almost from the very beginning of computers. The concepts that underlie the way machine learning works have been around. But it's really only been in about the last decade, since about 2010, 2011, that AI and machine learning methods have actually started to work really well. And there have been two reasons behind that. So the first is lots and lots of data. Where is this data coming from that we'll be able to make our machine learning methods better and better? It's coming from us. And in websites and social media, where we're providing a lot of content that can be used to teach AI and machine learning algorithms to be better at what they're doing. And so 350 million new photos are uploaded to Facebook every day. 500 hours of video are uploaded to YouTube every minute. 500 million tweets every day. And you'll remember that we talked about we need labels for our data to be able to teach our AI and machine learning approaches how to do different things. Well, when we're uploading pictures and video, often we're also putting like a caption about what's going on in that picture, or other people are commenting on what we're uploading and providing context about what's going on in those photos, or those videos. So those can be used to help infer labels and other things about it. One of the things that you may have noticed in interacting with the internet lately is the test that you have to do to prove that you're not a robot have gotten more and more sophisticated. So for example, right now, you may have to, if you're interacting with a website, have to identify where are all of the traffic lights in this picture? Where are all of the lane markers in this picture? Well, you can guess that maybe that data that you are generating and you are labeling as a human is being used in order to train future autonomous vehicles. So we are not only providing data, but we're often also providing labels for this data as well. And you saw a data set earlier on that had dogs and cats and things like that on it. Actually, one of the first big tasks that AI and machine learning approaches were really successful on was trying to distinguish between dogs and cats, although it's still a hard problem. And there's a reason for that. It's because the internet is made of dog and cat pictures. People love to post pictures of their pets, and people comment on them to be able to talk about how cute that cat is or how cute that dog is. We have tons of pictures of dogs and cats that we can use to train AI and machine learning approaches. So all of this data is one aspect that's making machine learning methods work really well now. The other aspect is really powerful computers. So we couldn't do anything with this data if we didn't have computers like the Summit supercomputer at Oak Ridge National Lab and the other supercomputers at other national labs, as well as the big cloud computers that are used in industry and various other clusters that Google and Amazon and all of these entities maintain. Computers now are faster and bigger than ever before, and they are also enabling us to be able to most effectively process this data and be able to build more and more powerful machine learning approaches. Let's see, I'm checking the chat. Does it mean you're hurting future machine learning research by failing the CAPTCHA? That's a great question. So what you're doing when you're doing that, you are providing labels, but I suspect that for any one particular image that people are using and doing CAPTCHA on, that they're actually using a lot of labels from a lot of different people. But if you were maybe labeling data for somebody explicitly and you provided the wrong label and you were the only person that labeled that data, that could hurt the performance of the machine learning approach. Yes, because it needs the label to be able to learn about what what's going on in the picture or the video or whatever it's trying to learn about. Great question. I'm also often very conscious about that when I'm selecting. It's like, oh, well, there's a tiny little sliver of a stoplight in that. Do I have to be careful? I too sometimes are failing on those captures. Okay, so how does machine learning work? Well, there's nothing magic about machine learning. Everything about how machine learning works is just math. And I've got a couple of examples of sort of math-based machine learning approaches that are on the slide here. We're not going to go too deep into any of the math today. And in fact, I'm going to tell you a little bit more about a specific subset of machine learning approaches that are actually my favorite types of machine learning approaches, which are nature-inspired machine learning. So you may remember that at Oak Ridge, I was part of the nature-inspired machine learning group. At the University of Tennessee, I am teaching biology-inspired machine learning. So I really like looking to nature and biology for inspiration in trying to come up with new ways to do machine learning. So what are some examples of nature-inspired machine learning approaches? Believe it or not, one way that we look to nature for inspiration is looking at ant colonies. Ant colonies are actually pretty sophisticated in what they can perform with very simple, very small individuals, the ants. They can still do really, really complicated tasks. So we take inspiration from ant colonies in a particular type of machine learning called ant colony optimization. We also take inspiration from flocks of birds and schools of fish in an approach called particle swarm optimization. We take inspiration from the way that particles behave under different conditions in an approach called simulated annealing. And then my two favorite, and the ones that I spend most of my time doing research on, are genetic and evolutionary algorithms, which take inspiration from genetics and evolution in the way that we solve different problems. And then the one I'm going to tell you a little bit more about today is neural networks. And neural networks, as you may guess, take inspiration from a very particular entity in nature, brains. So we're going to focus on neural networks today. So not only are neural networks my particular favorite form of machine learning, they're also one of the most popularly used in real world problems. So a lot of the examples that I gave you earlier, face recognition in an image, speech recognition, any sort of image identification, distinguish between dogs and cats, even a lot of the recommendation engines that are providing recommendations on social media sites and media content providing sites like YouTube and Netflix are driven by neural networks. So I am going to ask you all a question now. Looking at this picture, does anybody know what this thing in the center of the picture is? Hopefully you can see my mouse.
Cell or cell body?
It's the cell body of, do you know what the cell type is called?
A neuron.
It's a neuron, exactly right. So this is a neuron right here in the middle. And then coming out from the neuron, we have axons and dendrites. But then you can see these things that are sort of connecting between neurons. Does anybody know what those are called?
Yes.
Anybody have any thoughts what those are?
Synapses?
Those are synapses, that's exactly right. So this is a very sort of complicated cartoon level picture of what's going on in biology. In artificial neural networks, the types of neural networks that we implement in machine learning, we also have neurons and synapses, except they look a little less cool than that picture. So what we have here in our artificial neural network, each of these circles are neurons, and each of these arrows are synapses. And what happens is we're going to feed data into our neural network on our input neurons. You can think of these as sort of like sensory neurons where they're receiving information from the environment. And we're going to do some information processing through the network. We're going to talk about how that works in a moment. And then we have output neurons, which you can sort of think of how those is interacting with the environment in some way. Our output neurons as humans are like our motor neurons, which interact with the environment, interact and control our muscles to be able to actually have us be able to interact with the world. Typically, our output neurons in neural networks are maybe they're providing an action that will interact with the world, but maybe they're also answering a question like if it's a dog or a cat, or if it's a pig or not a pig. And then we also have hidden neurons, which are doing all of the sort of computation internal and doing sort of information processing from the input data that we're receiving to the output data that we are going to produce. So I'm going to give you an example of how this actually works. So pretty much any data that we would be trying to interpret, a picture, a speech pattern, videos, whatever, can be represented with numbers. In the instance of images or pictures, our numbers might be the pixel values, the red, green, blue values of each pixel in the picture. So we can represent the data that we're trying to interpret as some list of numbers. So here, my input data is going to be these three numbers, 30, 50, and 70. And what we're going to show here is what happens at one of the hidden neurons and how the calculations proceed through the network. Okay, so I said we weren't going to do any math. We are going to do a tiny little bit of math. So brace yourselves. I know it's Saturday morning, but get ready. So each of these synapses has an associated value. And here, the synapses that are coming out of each of these neurons have a value of 2, -1, and 1. So let's do the math for how this neuron will process information. We are going to do 30 times the synaptic weight value here. So 30 times 2. Then we're going to do the same thing here, and we're going to add that inside, 50 times -1. And then we're going to do the 70 times 1 at the bottom. And if we add all that up, we get 80 inside here. And then to figure out the number that comes out of this neuron, we're going to check to see if it's bigger than 0. And if it is, we're going to send that number out. Otherwise, we're going to send out 0. So in this case, the number is bigger than 0. So we send out the number. We send out 80, and that will be the output of this neuron. Okay, that was the math, y'all. Not too bad, right? Just some multiplication and addition and this fancy little thing that comes out at the end here, but still pretty simple. So if we change the data, if we change the picture that we're presenting or the word that we're saying, it's going to change the numbers that are going to come in. But the weight values here aren't going to change. They're still 2, -1, and 1. So if we do that same sort of math, the multiplication of each of these values, and we add it all up in here, inside here with these data points, we are getting -20 on the inside. So then 0 comes out of the network. So this is what's happening at sort of the single neuron level, but there's lots and lots of neurons in the network that would be processing this information in different ways simultaneously. And this is the math that's happening anytime a picture is being recognized with the neural network, or you are talking to your smart home assistant and it's interacting with your the sound waves that are being produced as you're speaking. It's doing this sort of math in the background, but it's just doing a lot of them. The neural networks that underlie image recognition and speech recognition tend to be really, really big, with hundreds of thousands, maybe even millions of neurons that are operating simultaneously. But the individual math level at each of the neurons is actually pretty simple. So the key thing that's happening with neural networks is the synaptic weight values. So remember that the data at the neurons changes as we change the picture that we're feeding in. The weight values stay the same. So the weight values are actually what are being learned or determined by the machine learning algorithm. Now, there's a particular machine learning approach called backpropagation that's used to figure out what the weight should be. So the math to do backpropagation is a little bit more complicated than what I showed you previously. It's based on an optimization technique called gradient descent that you would actually learn about in calculus. So if you ever take a calculus class, you'll learn everything you need to know to be able to do neural network training. So when we're teaching a neural network how to learn how to do a particular task, we use backpropagation to figure out what those weight values on all of our synapses should be. And the way that it works is we start with our collection of labeled data. You remember those flashcards we talked about earlier. This is a car, this is a plane, this is a dog. And we start with a network that knows nothing, that just has a bunch of randomly initialized weight values. And we start to feed the data through the different pictures. We do all of those calculations through the network, those multiplications and additions, and that little check at each neuron to see if it's greater than 0. We feed all the data through until we get answers at our output neurons. And we see how far away the value is from the right answer, from the label that we were expecting. This backpropagation approach then slightly changes all of the weight values in the network in order to be able to make sure that the next time I pass that picture through, the answer is a little bit closer to what it should be. And that's how we train neural networks. So again, you would learn that sort of math in a calculus class. They might not tell you how it applies to neural networks, but you'll have everything you need to know to be able to actually train and use a neural network. So with that, we are going to train and use a neural network right now. So I am going to post a link in the chat. I'm going to stop sharing this screen. So while I'm doing that, I'm going to ask everybody to go fetch maybe like 2 things from the room that you're in, like a toy in a book, or 2 things that you want to teach a neural network to distinguish between. And we are going to use Google's Teachable Machine to teach a neural network how to distinguish between those 2 things. And you are each going to pick your own 2 things that you want to teach it between. Does somebody have a question? All right. While you're fetching those things, I will go ahead and share the link that we went to. You can see here that in the example, the first example, the girl was teaching it to distinguish between her and her stuffed dog. And what we're going to do from Teachable Machine, we're going to click Get Started, and we're going to do an image project. And when you click on Image Project, it's going to have you we're going to do a standard image model. So I'm going to stop sharing my video on Zoom, which hopefully you can still see my screen that I'm sharing. And I'm going to turn on the webcam here, so now you can see me in the kitchen that I'm currently located in. And I am going to teach my neural network to distinguish between 2 entities. And the first one is going to be this little stuffed pig. Can you tell that I like pigs from the presentation? So I've got a little stuffed pig here. And so what I'm going to do is I'm going to hold the stuffed pig up in front of the webcam, and then I'm going to click Hold to Record. And I'm going to collect a bunch of pictures of this pig, further away, closer up, rotated in different ways. And you can see here that in that little short time, I collected about 215 images. So that's going to be my pig class. Now down here, I'm going to use another class that I want to teach, and that's going to be the Baby Yoda. Big Star Wars fan, can you tell? And I'm going to do the same thing with Baby Yoda. I'm going to rotate around a little bit, get closer, get further away, rotate him around. I know his name is Grogu, but I'm still going to call him Baby Yoda. Okay, so I've collected about 180 images of Baby Yoda. Now, that's my data. That's the data that I'm going to use to teach my neural network. So we're ready to go here, and I can click Train Model. Now, this may take different amounts of time depending on the computer that you're running on, because this is actually training on your computer. And you can see eventually it will start training. And it's going to do 50 iterations. It's going through 50 iterations of that back propagation process to try to get the model trained. And now, hopefully you can see, it thinks I'm Baby Yoda, which is very flattering. I'm going to hold up the pig, and hopefully you can see that it is correctly identifying this as the pig. And now, Baby Yoda, and it is correctly identifying it as Baby Yoda. So, if you are comfortable sharing your, or turning on your camera, I would very much like to see what you all are doing and what you're distinguishing between to see how your neural networks are working. So please feel free to do that. And please feel free to also tell me and let me know what we're teaching your neural network to do. If you happen to have like a cat around, I see an orange and apple, or what is it? Is it an apple? What is it? No, mango, mango?
Yeah, it's a mango.
Yeah. Water bottle, nice. You can also do different like hand gestures, like a thumbs up or a peace sign or something, to have it distinguish between that if you don't have any objects around to train against. One of my favorite examples, if you happen to have a younger sibling hanging out in the immediate area and or a parent, oh, there's a puppy. That's my favorite when you get the pets involved. You could also drag them into to have it distinguish between you and your sibling. So the favorite example for those is now you could train a neural network so that anytime you have a sibling that walks by, you could write some code to have your computer do something weird, like make a sound or something. Because you now have the ability to train a neural network to distinguish between different things. So lots of cool things you could do with that. Anybody else have any examples that they want to share of what they're teaching and how well it's doing? Is it not working for anybody? Pencil in a book, nice. Both the same color, that's interesting because it may just be using color to distinguish if you don't have two things that are different colors. Tub of moisturizer, jar of chocolate chips, nice. Oh, Thomas is doing the hand gestures of whether or not you have your hand on your face. So one of the cool things, and I'll share my screen again. One of the cool things that you can do with this, if you happen to be logged into a Google account, you can save the network that you train to your Google Drive, or you can download the project and open it back up later. So that you can reuse the same network that you've trained before. You can also, if you're familiar with coding, you can export the code in different formats. Like you can export it into a Python format and load it into a Python script that you write. So with that, now that you've actually played with machine learning, you've seen it in action. I'm going to go back to my slides. I'm sure you will all still be training and playing with that, but it's fun. It's fun to play with it. So I wanted to briefly talk about algorithmic bias. So it's already sort of mentioned a little bit, and there's my dog, her barking. I am going to attempt to, let's see if you can hear my sound. I may have to reshare. Can you all hear that?
No.
No, okay. I'm gonna stop sharing and reshare. I'm not going to be able to share it. I'm going to share the YouTube link in the chat, and then we can. I encourage y'all to check that out later. Talking a little bit about bias in machine learning. Now, the thing that we want our machine learning approaches to do is be able to accurately give us answers for our particular task. So in the pig example, correctly say that it is a pig or not a pig most of the time. But we also want it to be robust. We want it to cover a variety of different cases. So we talked about how pigs come in all sorts of different colors and spots and all sorts of different things. We also want our machine learning approach to be robust to the different types of pigs there are, to be able to give us the correct answer, even when the pigs look different from each other. So in machine learning, what we're actually giving the computer to learn from, the data that we're giving it is really, really important. And it's essentially the coding that we're doing when we're using a machine learning method is the data that we're providing. So it's our job to make sure that the data that we're providing is comprehensive enough so that we can avoid as much bias as we can. So AI and machine learning approaches only know as much as we tell them from our data. So when you are coming up with your data set, like when you are training your neural networks that you may still be working on right now, your data set should be pretty large and it should cover a bunch of different possible scenarios. So you notice that when I was training my example, I not only sort of held the pig up in front of my face, but I rotated it in a bunch of different directions. I held it closer and further away. I was trying to give it a bunch of different scenarios that I might be presenting to it in the future. Now, we talked about a bunch of different ways that machine learning is being used and that you might be interacting with regularly. So if you were training a machine learning method to do something like face recognition, you would want your data set to represent people from all races, all ages, and all genders equally. This has not been something that AI and machine learning, the field and the data sets that we have, has done particularly well so far. So oftentimes our machine learners, our algorithms will be biased because we don't have enough representation in our data sets. For voice recognition, we would want to train our smart home assistants, again, I won't say their names just to not wake them up, with various accents of English and with various voice tones. So if you have an accent, so I have a Southern accent, if you have an accent because of your native language, you would still want your smart home assistant to be able to understand you. And so in your training, in your data set, you would want to make sure that you are capturing all of those different accents and tones of voice, higher voices, lower voices, so that your machine learner could still be able to predict correctly. In the pig or not a pig example, you would want pigs of all shapes and sizes. Now, machine learning is being used in a lot of different, thanks, you're Aspen, that's great. In a lot of different places. So one of the examples, one of the real world examples where machine learning is being used is in deciding whether or not to give somebody a mortgage to be able to buy a house. And in that case, it's really important that our machine learning algorithms be fair in deciding whether or not that mortgage should be given. And that's the sort of scenario where it's very, very important that our data set be representative. Another example where machine learning is being used is in the medical field. And in that case, the data sets that we would be training from, we would want to make sure, for example, if you were trying to train a machine learning method to look for an anomaly in an X-ray, you would want to make sure that the data set that you were training with had plenty of examples of people of all different shapes and sizes, genders, races, etc., to make sure that the machine learning algorithm would perform correctly in diagnosing anomalies in an individual. So we have to make sure that we are conscious of what data that we are providing to machine learning algorithms, and as we're using them in the future, to try to make sure that we're being as fair and keeping our algorithms as unbiased as possible. Okay, so now the key takeaways from what I've been talking about is that machine learning is being used across a wide variety of different fields, from entertainment to medicine to transportation. You're interacting with machine learning every day, whether or not you knew it before, although it sounds like a lot of you already had a good intuition of when you were interacting with machine learning. So it's important to understand when you're interacting with a machine learning algorithm, how it might be collecting data from you, and when you are providing labels and data to a machine learning algorithm, so that you're conscious of why a website is providing you the content that it is providing you, for example. Okay, so now that we've sort of gone over machine learning as a whole, I wanted to very briefly talk to you about some of the research that I do. So in addition to using machine learning for things like classification, face recognition, speech recognition, my research group does a lot of work with machine learning in teaching neural networks specifically to do different things. And in this case, we taught the neural network that you see on the left of the slide, where you see the circles are the neurons. We have all the little edges connecting them. Those are the synapses. We taught this neural network to play the Atari game Asteroids. And you can see it navigating throughout the environment and shooting the different asteroids. And actually, this particular neural network was fairly aggressive in how it plays the game. It gets very close to the asteroids in the environment, so much so that it occasionally will die just because it gets destroyed by the shrapnel of the asteroid that's being destroyed by when it just shot it. So this is one example. We actually use games a lot like Asteroids to be able to test our machine learning algorithms to see how well they're performing on different tasks, because it's a pretty simple representative environment. So a couple of real world tasks that we do. So this one, again, I mentioned that I love robotics and droids. In this case, we actually had a couple of students at the University of Tennessee who did a project where they wanted to train a neural network to perform an autonomous robot navigation task. And so the goal for the robot, this is the robot, its name is Neon. The goal for Neon was to be able to drop Neon in an unfamiliar environment, like a new location that it had never been in before, and have it be able to navigate and explore that unfamiliar environment while avoiding obstacles along the way. So you can think of this task as maybe being something like a search and rescue task or a surveillance task, where you're dropping a robot in an environment and you want it to run around and cover everything in that area. Maybe it's looking for a particular thing, but you also don't want it to run into any obstacles because it might hurt itself. You can also think of this as a smart Roomba. You want to be able to put your Roomba in your room, cover as much of the ground in the room as possible. You want it to vacuum everywhere, but you also don't want it to like bump into the cat along the way, because that could be bad. So the challenges for this, we were going to give the robot no explicit instructions on how to operate. So this particular robot has a LiDAR sensor on the front. That's essentially its eyes right here. It's on a little servo, so it goes back and forth, sort of looking in front of it in the environment. That's the information that it's receiving from the environment. And then the neural network is providing motor controls to the robot. Left motor forward, left motor back, right motor forward, right motor back. So at the beginning, we haven't taught it how to do anything. It doesn't know anything to start with. It doesn't even know how to turn left and right. It has to learn how to do that over the course of training. And we were going to train it only in simulation. So this is what the simulated environment looked like. It's very, very simple. The robot is modeled as the red sphere. The obstacles in the environment are modeled as the blue spheres. And we're showing the ground that the robot is covering with the highlighted squares. Now, of course, the robot doesn't know the highlighted squares. It only knows what it sees from its LiDAR, whether or not there's an obstacle in front of it. It sort of has to remember where it's been before to try to cover more and more ground in the space. So we did all of this training in simulation. And then because it's machine learning, remember one of the key things about machine learning is we want it to be able to generalize to new environments that it's never seen before. And in this case, we wanted it to not only be able to generalize to new environments with new obstacle layouts, but we wanted it to actually be able to generalize from simulation into the real world. So this is actually the space right outside my office at the University of Tennessee. When they did these testings, the professors just pulled whatever was in their offices out to act as obstacles. And you can see this was the very first time they tested Neon in the real world. It is navigating and driving throughout its environment controlled by the neural network, and it is avoiding obstacles that are more complicated obstacles than what it saw in the virtual environment along the way. So this is one example of how we're using machine learning in we call these control tasks, where it's interacting and controlling something in the real world to perform a particular task. Another example is a small-scale autonomous vehicle project. So this is our 1/10 scale Formula One race car. That's me sitting with it, doing some testing. And this picture was taken in November. This is where we're still actively working on this project. And in this case, we're training a neural network to be able to drive this car around a racetrack. So again, we're training in simulation, just like we are in the autonomous robot example that I showed you previously. Hopefully you can see in this video, there's a little black dot driving around the track here. That's the car, the simulated car in the simulated environment. And we actually trained it on 1/10 scale real Formula One racetracks. Now it's worth noting, I know literally nothing about Formula One. This is a racetrack called Catalunya. I don't even know if the car is driving in the right direction around the racetrack, but it's driving around the racetrack and it's not running into walls, which is all that I really care about. So yet again, we wanted it to be able to take what it learned in the simulated environment and translate it into the real world. And so of course that meant that we had to build a racetrack. So this is one of the racetracks that we built at Oak Ridge National Lab. And this is the car. The car doesn't have a name. We're taking recommendations and suggestions for the name for the car. But you can see that it is, in fact, driving around the racetrack that we assembled. I will note the tape on the ground, a lot of the tape is not tape that we put down. The blue lines are just distance measures for us to see how far the car was able to drive. The car can't see that. It also has the LiDAR, but a more advanced LiDAR that's spinning on top of the car. And that is what we're getting from the environment as the sensor. You can see, sometimes for research, you have to do things like build a racetrack. And in fact, for this particular project, I have two amazing high school students from Oak Ridge High School who are working with me, Amelie Nagel and Alex Shanafield. They have actually written some papers with me on the car research, and we are going to be building a racetrack tomorrow at Oak Ridge High School to do some more car testing. So this sort of research on neural networks as applied to control problems is pretty accessible to high school students. So if this is something you're interested in engaging with and would like to learn more, I would encourage you to reach out to me. Actually, their project, you'll notice that the car is not going as fast as you might want a race car to go. Their project is make the race car go fast. So we're doing testing tomorrow to see how fast we can get the car to go. And with that, I will ask now if you all have any questions about AI and machine learning, if you want to learn more about my research, or just sort of questions about how I became a computer scientist and entered this research field. I'm happy to answer any questions you might have. And if you're interested in learning more, please feel free to contact me. My email address is right here across the bottom of the slide. Thank you very much.
Awesome. Thank you so much, Katie. That was so informative. If you guys have questions, feel free to enter them into the chat, or if you want to ask your question out loud, turn on your camera, unmute yourself, and you can ask your question.
What would I suggest studying in college to learn about machine learning? Computer science would be the top in the majors that would be most recommended for machine learning. There are some programs that actually have majors in machine learning or artificial intelligence now, or minors in that space. Math and computer engineering are also very relevant topics to the field of machine learning. Obviously, again, math underlies pretty much everything that we do. But most machine learning, we're coding it up, writing programs, interacting with data. So computer science would be the primary topic that I would recommend studying. Of course, I'm a little biased as a computer scientist myself. So
Awesome, thanks.
Ferrari, like Ferrari, is that Julie? Is that what you're getting at for the name? We had not come to that yet. Is calculus the most applicable in math to machine learning, or other types useful? Calculus is really important for things like gradient descent, but most of neural network operation on actual computers is implemented using linear algebra operations. So calculus, linear algebra, both very, very important to implementing and using machine learning methods.
There was a question in the chat earlier. They asked if you're hurting future machine learning research if you enter CAPTCHAs incorrectly.
Yeah, so I mentioned earlier that typically for CAPTCHAs, they're using multiple people's responses to label the images, but there's a lot of opportunity actually for people to provide labels for data sets for machine learning. And if you do provide the wrong label, like if you created the data set for that neural network that you just trained and you gave it the wrong label for the data that you were providing, that would really hurt the ability of the neural network to perform the task that it's trying to perform. Yes, yeah, linear algebra, you got the midterm on Monday. It's important. It's very useful in the field of machine learning. So it's good to have that knowledge. There are a lot of movies that feature robots and artificial intelligence. How much of that is true and how much of that is fiction? It's really, in movies, it tends to be really advanced. Particularly, you can see the sorts of robotics and autonomous vehicles work that we're doing today. And you've probably heard in the news about things like autonomous vehicles. It takes a lot to teach a computer how to do different tasks. And so one thing that you might have noticed is that each thing that we talked about only did one task. it only was able to, like, say, distinguish between cats and dogs, say if it's a pig or not a pig, do speech recognition, drive a car. The same machine learning method that we taught to drive the car can't also distinguish between cats and dogs. So there's a sort of distinction there, in that we very specifically train our AI and machine learning approaches to do one particular thing at a time. And they're not very good at learning how to do lots of different things simultaneously. So in movies and TV shows, the sort of AI that you might encounter can do a lot of things really well. That's an idea called general AI. We're not there yet, and I think we're quite far from having something that can do lots and lots of tasks really well simultaneously. How large are data sets for machine learning? Usually like thousands of images. Yes. So you saw, for example, that we trained a neural network that did pretty well on just maybe a couple hundred images that it was training with. But typically the machine learning algorithms that we're training have hundreds of thousands, maybe even millions of data instances that are being used to train. And part of that is to make sure that we're giving it lots of examples to learn from, to do more sophisticated tasks than we were doing in that distinguishing between two. But we're working in the field of machine learning to be able to build machine learning methods that require less data to be able to train on. So this is actually a big problem if we want to teach something where we don't have a lot of examples that we want to teach it to train against. But we're still working on how to actually do, that's an active area of research in the field. How long does it take for the models to train? It depends. So it depends on how much data you have. And in the simulated environments for the cars that you just saw and the autonomous robot, there's a couple of hours to train for each of those on like a workstation. It wasn't on a supercomputer. But for large scale machine learning models, like those that are doing speech recognition on your smart home assistants, that would be like hours to days on some of the largest computers in the world. Do I have any resources for learning more about machine learning? I can point you to a variety of YouTube series that are really good. The one that I would recommend most is called Crash Course AI. I will try to put a link in the chat. That you may have watched other Crash Course YouTube series. There's lots of them across lots of different topics. The cool thing about Crash Course AI is that they actually do labs where you write some AI and machine learning code along with them, and they teach you how to do different tasks during the YouTube series. I will try to pop a link in the chat for you. And I will say I'm a little bit partial to that one because some of my friends created the course. So let's see, I think this should take you there.
Someone asked, do you recommend any research or intern program opportunities for machine learning for first-year undergrads?
There are a lot of machine learning opportunities across the national lab systems. So I would check out the internships for undergraduate students through the Department of Energy National Labs. There are also opportunities in some of the defense labs as well. So if you happen to have like an Army research lab or an Air Force research lab in your area, those are also opportunities. But my first recommendation would be the Department of Energy internships.
And we're going to talk more about the Department of Energy internships before we leave today. So yes, it's a good reminder. All right. How important do you think coding is for students to start doing in middle school and high school if they're interested in machine learning?
If you have the opportunity to start learning some coding now, that would be fantastic. Even if your machine learning is not what you're most interested in, most fields today use coding of some form. Everything from biology, chemistry, physics, everything in science is using coding to be able to process their data, analyze the different data sets and do simulations of different environments. But also, coding is actually being used across a variety of the humanities fields as well, in literature and writing and art and music. So even if you're interested in those areas, coding is fantastic to learn as a general skill set for whatever you happen to be interested in. Yes, I can explain how the evolutionary methods of machine learning work. That happens to be my second favorite algorithm, and I combine evolutionary algorithms and neural networks in my research. That is my research area. the evolutionary approaches are actually pretty simple. I'm conscious that we're running out of time. What you do in the case of maybe you want to evolve a neural network, which again is what I do in my research, what we start with is a bunch of random neural networks to solve a particular task that form our initial population, just like a bunch of them, like hundreds to thousands. And we take each of those and we have a fitness score for each of them. So if we have a task that we're trying to get them to learn how to perform, we sort of run them through their paces to see how well they perform on that task. So how well it drives a car around a racetrack, for example, can give us our score for how well it's performing. We use those scores to then do basically survival of the fittest. The ones that are pretty good tend to have more offspring, and the ones that aren't as good tend to have fewer offspring. And they create offspring. We do things like mutations and recombination that you might have learned about in biology, where we take two individuals and then they have children that inherit characteristics from both of those individuals. And it continues along that process. And it sounds pretty simple, but using that sort of approach actually improves the performance over the course of generations. We call them generations in evolutionary algorithms. And they get better and better at solving the tasks. It's one of my favorite. I just finished teaching it in my course. That's what I do my research in. So I love that. If you're interested in learning more about those, please let me know, because I'd be happy to talk more about them and I send you to resources on those as well.
Great. I agree with Anna. I wish that I had had Katie as a professor in college.
my students get me to nerd out in front of them about all these topics every Tuesday and Thursday. I get this excited talking about everything. So
I can tell. Does anybody else have any other questions before we wrap up?
I will put my email in the chat if you are interested in reaching out. Happy to talk more if you would like some more resources.
Awesome. Thank you for that. All right. I'm going to turn it back over to Julia. Katie, thank you so much. That was super informative and interesting. Yeah,
Thanks.
Great talk. Thank you so much. And we turn it over to Julia.
Thank you very much. Thank you, Alison, and thank you, Katie, for the great presentation. And Alison, good job for picking this topic and inviting Katie to talk with us. So that was great. Thank you very much. A few reminders before you leave, because as you asked about internship, we would like to remind you about the possible internship, the possibilities that there are at the national laboratories. So especially for college students, but also for high school seniors, because since this happens every year, you need to start planning as early as all of this year. So there is the Slack LTLS internship. I'm gonna write down, no, I'm gonna actually put the link in the chat if I can. Here we go. This is the LTLS internship. Oh,
I think I already put it in there.
Doing it. Perfect, thank you. So there is the LTLS internship, and the application deadline is March 1st. New internship opportunity for the Department of Energy, deadline February 17th, so pretty close. And there is a link in the chat as well. And if you have any questions, feel free to write at stagecamp@slack.stanford.edu, and you can answer all the questions. We shared all these links also in the past Page Live events, and we are, and as we say all the time, we are trying to help you find an internship. So let us know if you are looking for it. One more thing, make sure you keep your SAGE network alive. So be part of the SAGE community, where there are a lot of students and professionals that are supporting each other, and they are leading you towards exciting careers. So take advantage of this network. Make sure that you tell your friends about the SAGE Live, and tell your friends also about the possibility of participating to a SAGE camp. And all the information, the SAGE camp is, all the SAGE camps in all the national labs are are getting prepared, and there are a lot of information in our website that is www.mystatejourney.org. And I'm going to write it in the chat as well. And you can find all the information about the summer camp. Again, thank you everyone for joining us this Saturday. That was fun. That was really interesting. Now we know where to start with machine learning and artificial intelligence. Thank you, Katie, for the great presentation, and thank you all the students for participating. We hope to hear from you soon. Thank you, everyone. Have a great day. Have a great weekend.
Thank you. Bye.
Thanks very much.
Thank you so much.
Thanks, everyone.